All right. Now that we have conservation of mass, we need to do conservation of linear momentum. Right? Which apparently I've written in blue. All right, now, remember the conservation of linear momentum says that the momentum of a system is conserved by the forces on a system. Okay, and we can do it all in vectors. All right, and just like we did for conservation of mass, what we're going to say, by the way, it's obviously a derivative, right? What we're going to say is that this term can be thought of as a rate of accumulation of momentum in a differential control volume plus the net flux, which is the flux out minus the flux in of linear momentum. Okay, now this one's harder, just like it was when we did volume approaches, because it was done in multiple has multiple vectors, right? We can do it x, y, z. So we're going to derive all the equations just in the x linear momentum, and then when we get to the end, all right, we're going to when we get to the end, we'll write them all out in all three directions. And the other thing I want to say is this is right. We're going to call this part one. All right. So we're only going to deal with in part one a little bit of the rate of accumulation. All right. So that's part one, rate of accumulation. All right. So what is it? So remember, we got this. We need to think about how much linear momentum is in our volume. All right, and so again, this is actually relatively straightforward. We need the mass of our system times the volume of our system, or the mass of our system times the velocity. All right, so roughly speaking, we have mv, right? And however, given what we're talking about here, again, we're going to think about this not as mv, but we're just going to think about the x direction, so u, okay, the velocity. All right, so the momentum, if we had some control volume, I'll draw it over here. All right, and here's x, z, and y, and again we have dz, dx, dy. All right, then m of that control volume is really rho, right, times dx, dz, dy, and then times u to get our momentum. And again, if we're talking about the rate of accumulation, we're thinking about that in terms of d dt, right? Then we can think about this term essentially as just d dt of rho u. I'll move those up here so we like that better. Rho u. And that dx, dy, dz, right, those aren't changing with time, so they can stay out of the derivative. All right, so this is right here, this in this red box, that's rate of accumulation of linear momentum in our control volume. So that's part one of deriving these equations.